Okay, all right, let's recall what we had last time. So right now we have fundamental theorem of calculus, which says the definite rule a to b integrated fx dx, which is fx, the difference of the two function values at the boundaries, okay, a and b. So this is the fb minus fa, where this capital F is an arbitrary antiderivative of little f. Arbitrary antiderivative of little fx. Okay, it's determined only up to constant. Okay. Now a special case. So if we take this fx to be capital F derivative, okay, then we can easily find if fx is the chain rate, okay, is derivative of some function with respect to a variable x, then we can actually find antiderivative. So antiderivative, which has antiderivative. Capital F, okay, by definition of antiderivative, that's easy. Then we can get this, okay, i.e., we integrate the chain rate. If we integrate chain rate, then we get, now apply fundamental theorem of calculus, fb minus fa, okay. So this is the net change, okay, net change. The right side is net change. Then this is the net change theorem. It's just a special case of a fundamental theorem of calculus. That's very easy. Okay. Now examples of this net change theorem. Example. When the velocity is the change rate of position function, okay, position function, ds over dt. Okay, velocity is change rate of position function with respect to time. So if we integrate, so velocity, instantaneous velocity. So s equals st is position function of some object, position function of some object, a particle or something. Okay, then we apply the net change theorem. Then if we integrate velocity from a to b, velocity vt dt, then we get the net change sb minus sa, i.e. the position at time b minus the position at the time a. Okay, so this is final position, this initial position. So the change of position is also called displacement. Okay, so this gives us the displacement. Okay, this gives us displacement. I.e., if we integrate velocity with respect to time from initial time to final time, then we get the displacement during the period. Okay. Okay, another example. Acceleration. Okay, acceleration at is velocity derivative. Okay, the velocity, change of velocity with respect to time. Okay, acceleration. So then if we integrate the acceleration, then we get the net change of velocity. So then we integrate t1 to t2, integrate at dt. Then we get a vt2 subject vt1. Okay, this is the right side is the net change of velocity. The net change of velocity. The right side is net change of velocity. So final velocity minus initial velocity. Net change of velocity. Okay. Another example is, for instance, there are a lot of examples. If you study chemistry, then you care the concentration of a certain chemical product in a reaction, okay? So concentration, C, the notation is C, concentration of a certain, okay, so it's concentration, this is the concentration of some product in a reaction, okay, in a chemical reaction. Okay, at time t. Okay, now how fast a chemical reaction is, we use the change rate of a concentration, okay, concentration. Now there are many factors that actually affect the how fast a chemical reaction, goes on, okay, how fast a chemical reaction is, okay. There are many factors like a temperature, like pressure, etc., etc. Okay, then from T0 to T1, if we integrate the change rate of concentration, the derivative of concentration with respect to time, then we get the net change of concentration, T1 minus T0. Okay. Okay. For more examples. Suppose the change rate of population, okay, if the rate of growth of population is dn over dt, then so here, although the population is not continuous, okay, it doesn't make sense. Or instantaneous derivative, what instantaneous derivative is, because here it's not continuous. You cannot see 1/3 of a people, okay, 1/3 of people, a fraction of a human being. It doesn't make sense. Okay, however, we can view roughly as, as a continuous function if we study large population, okay. So we can formally view it as, does not change too much, okay. Although it's discrete, we can still view it as an approximation by continuous function, okay. So here you cannot think this as instantaneous change rate, okay. It doesn't make a sense if you think in that manner. Then you integrate T0 to T1, initial time to final time. You integrate the change rate, okay, integrate the change rate. Okay, then what you get is NT1 minus NT0. Now, a way to remember this is the net change theorem. To understand the net change theorem is the following. So here, so the left side, look at the left side of this equation. So formally, we cancel dt with dt, okay. So we have dt in denominator and dt in denominator, so we cancel each other. then you see we formally have this dn. Okay, remember d and this thing cancel each other. They are inverse operation, cancels each other. They are inverse operation, so they can cancel each other. So finally, by fundamental theorem calculus, you get this is n t1 minus n t0. Okay, by fundamental theorem calculus. Okay. Example. Okay, for instance, example. If the this case, suppose we have a rod, then the mass of a rod measured from the left side, its mass is mx. Okay, is mx. Now the linear density, how this mx changes with respect to linear length. Okay, x with respect to x. So this has x. So this is x. The length is x. So this is the mass of this part of the interval 0 to x. Okay, the length of this the left side from 0 to x. So mx is the mass of this segment. Okay. Then we have linear density. Linear density rho x is defined as the change rate f m prime x, or you write as dm over dx. Okay. Then if we integrate the linear density from a to b. Okay. Then from a to b, x from a to b. So this gives the part of the mass of the rod for this part a to b. Okay. For instance, this is a, this is b. Okay. Then the mass is, we integrate the linear density rho x. What we get is m. So its antiderivative is m. So what do you get is mb minus ma. I.e., the part that so mass of the part 0 to b, subtract the mass of the part of the segment 0 to a. Okay, then if they subtract, then the remaining thing is the mass of the piece a to b. Okay, mass of the piece. Of the segment a to b. Okay. Let's see one example. Okay, another thing I forgot to mention is if we integrate speed. Okay, be careful. Speed and velocity can be different. By speed, we mean the magnitude of velocity. Remember, velocity, velocity can have direction. Either it can be positive or negative. But speed is only non-negative. Okay, it has no direction. So if we find the total distance traveled, okay, if we integrate to calculate the total distance traveled, then we need to integrate the speed. Okay, total distance traveled. During T1 to T2. Okay, it's possible that a particle end up at its initial position, a particle end up at its initial position, then its displacement will be 0. The change of position is 0. However, the distance traveled may not be 0. Okay, may not be 0. Okay, so let's see one example. Suppose we are given Vt. So suppose a particle is moving along a straight line. Along a line. At time t, its velocity, so that is the velocity at time t. Its velocity at time t is given by Vt is t squared minus t minus 6. So the unit is meter per second. Then per A, find the total displacement. During the time period 1 to 4. Well, how this graph of velocity looks like? How does this velocity looks like? Okay, velocity is a quadratic. So t squared Vt here, Vt is t squared minus t minus 6, which is if you factor this t minus 3, t plus 2. Okay, if you plot this graph, it's a quadratic with 2 roots, 3 and negative 2. 1, 2, and negative 2. 1, 2, 3. When t is 0, this is negative 6. 1, 2, 3, 4, 5, 6. Okay, so let's suppose here. So it will be look like this. Okay. So we don't plot the part t is negative. We start from t to be 0. So this is negative 6. So this is the t time 1, 2, 3, and then this is the v. Now here you see the velocity from t to be 0. The velocity is negative. And then velocity keep being negative until it changes direction at 3. Okay. So suppose the particle is starting point is here. So starting point. Suppose this starting point. Initial position. This is starting position of this particle. Then it moves. Suppose this is the we put this. Let's choose it to be 0, x-axis. Then it moves in negative direction. Okay, the particle has a velocity negative when t is 0. So it moves left. Okay, moves negative direction. Then when the velocity change direction, the velocity change direction at t equal to v3. So this is the t equal to 3, t equal to 0, right? T equal to 0. Then the particle starting move backwards. Okay, move backwards, positive direction. Okay, positive direction. Okay, so the displacement. How do we calculate displacement? Displacement from 0 to 4. Well, we just integrate straightforward velocity. Okay, velocity. So we integrate the velocity from initial time, final time 4. From 1 to 4, we integrate velocity vt dt, and then we substitute the vt, the given expression. 1 to 4. Vt. Remember, vt is t squared minus t minus 6 dt. Okay. Now you see from the picture, it looks like it should be from 1 to 4, from 0 to 4. From 1 to 4. It seems the area is, we get the negative contribution. So the displacement should be negative. Okay, let's see. So now we apply fundamental theorem of calculus. Fundamental theorem of calculus says we find antiderivative. So use power rule, 1/3 t to the power 3 minus 1/2 t squared minus 6 of t. Now we evaluate at the two endpoints and then subtract. Okay, then we plug in 4, plug in 1. Plug in 4, then we get a third 4 cubed minus a third 4 squared minus 6 times 4. Plug in 1, then we get 1/3 minus a half minus 6. So this we get 64 over 3. This we get 8. This we get 24. This we get 1/3. This we get minus a third plus a half plus 6. Okay, 64 minus 1/3. Then we get 63 over 3. So we get 21. And then minus 32 plus 6 plus 1/2. Okay, so this we get, this is -9 plus 6 plus 1/2. So it's -3 plus 1/2. Okay, did I make mistake? Okay, then finally what we get is -3 plus 1/2. -3 plus 1/2. So this will be -5 over 2. Okay. Okay. All right. Let's see some more examples. Let's part B. Let's see how do we find the total distance traveled. We find the total displacement. Now, what is the total distance traveled? Find the distance traveled. Find the total distance traveled. You're in 1 to 4. As we mentioned earlier, so the particle change direction is the particle change direction. Initial position, and it moves t equal to 0, and then at t equal to 3, it changes. Sorry, it's t equal to 1. T equal to 3 is change direction. It change direction. Now at t equal to 4 is still positive. So we need to calculate the distance traveled from 0 to 3 and from the distance from 0 to 4. Okay. Okay, so we need to integrate velocity from 0 to 3 and integrate the velocity from 3 to 4. Okay, this part from 0 to 3, you see, when t is from 0 to 3, look at the graph of velocity. When t is from 1 to 3, okay, t is from 1 to 3. Okay, then you see velocity is t from 0 to 1, 1 to 3. Velocity is vt is negative, okay, it's negative direction. So then we absolute value of velocity should be negative v, negative vt. Now velocity from 3 to 4 is positive, plus vt. We take off this absolute value. Then we plug in. So we want 1 to 4. Okay, that's right. So this will be 1 to 3 negative t squared minus t. Okay, sorry, I did forget something. Yes, that's correct. That's correct. Okay, so it's minus 6 dt, and then 3 to 4, it's t squared minus t minus 6 dt, and we apply fundamental theorem of calculus. So this will be negative 1/3 t cubed minus 1/2 t squared minus 6t from 1 to 3 plus 1/3 t cubed plus minus a half t squared minus 6 of t from 3 to 4. Okay, and then if you calculate the thing, so this it's better use computer package. So we avoid that thing is a computation. So it's a plugging the numbers by fundamental theorem of calculus. Then we just somehow cheat it a little bit. So we get this. Okay. The unit, don't forget the unit is meter. Okay. Okay. Now let's see another example. Okay, linear density problem. So suppose we know the linear density of a rod of length 4 meters is given by this. Okay, suppose we have the linear density. The linear density of a rod of length 4 meters. 4 meters. So suppose it's given by rho x, which is 9 plus twice square root of x. Okay. So unit is measured in the unit kilometer per meter. Kilogram per meter. Kilogram per meter. Okay. Kilograms per meter. Where x is in meter. Where x is measured in meters. From the left side, from one end of the rod. Okay, the question asks, find the total mass of the rod. Find the total mass of the rod. Okay. Well, this 4 meters. 0, and now suppose this is x. The linear density, rho x. Okay, rho x. So this is the 0, this is the 4. Okay, this is the 4. Okay, suppose this is x, then the linear density is rho x, which is 9 plus 2 root x, which is the dm over dx. Okay, now to get m, then we do antiderivative. So we integrate by the net chain theorem. We integrate the linear density from 0 to 4. Okay, then we get m4 minus m 0. So this M0 is simply just 0. So this is the M4. So M0, because at 0, there's no rod, so there's no mass. The mass M0 is 1. So this part equals 0. So this is total mass of the rod. Okay, essentially, what we need to do is we evaluate this definite integral 0 to 4, 9 plus twice the root of x. Excuse me, dx. Okay, so this is the total mass of the rod. Okay, now this becomes, we find antiderivative. 9 has antiderivative 9x. Now 2 root x, what antiderivative it has? And remember, root x has power 1/2. Okay, to do antiderivative, we need to increase the power by 1 and then divide. Okay, increase the power by 1. So power 1/2 increased by 1, 3/2. Okay, and then divide by 3/2. So we multiply 2/3. Don't forget this 2. Okay, and then we evaluate at 0 to 4. So this is 9 times 4 plus 4/3 times 4 to the power 3/2 minus when x is 0, then every term is 0. Then we get this is 36 plus 4/3. Now 4 to the power 3/2. Then this we get a square root 4. We get a 1/2. Then we get a 2. 2 to the power 3. Then we get a 8. Okay, so we get this is 36 plus. Okay, so this will be 46 and 2/3. Now what's the unit? The unit is kg. Okay, the unit is kg. It's a really heavy rod, over 40 kilograms. Another example. Okay. Suppose water flows from the bottom of a storage tank. On bottom of storage tank. So the rate at a rate of RT, which is 200 minus 40. The unit is liter per minute. Unit is liter per minute, where T is from 0 to 50. Okay, so the rate as so if T is 0, then we get a 200. The 200 liter per minute. And then when T is 50, then RT will be 0. Okay, so if you find RT will be when T is 0, so we get a 200. Suppose it's 200. When T is T is 50. Suppose 50 is here. 50 is 0. It's 50. Okay, now the area under the curve will be the water. Okay, water that flowed from the tank. Okay, so the question is find the amount of water that flows from the tank. Okay. During the first 10 minutes, the first 10 minutes, 10 minutes, 10 minutes. Okay, so what we do is we integrate integrate the rate, okay, to get the total amount of water, okay. So we start from 0 from n at 10, okay. We integrate RT dt with respect to t. This gives us the total amount of water that flowed from the tank. Now it ends at 50. Okay, the 50 is in minutes. Okay, so we don't need to worry about upper limit, lower limit. So it's 0 to 10. RT is 200 minus 40 dt. Now its antiderivative is 200t minus 2t squared from 0 to 10. And then we plug in 0 and 10. Plug in 10, so we get 200 times 10, 1 to 2 times 10 squared, minus when t is 0, then everything is 0. So then we get a 2000 minus 200. So we see we get a 1800. Unit is liter. Okay. So we have this many liter of water flow from the tank. Okay, then we are done for this section. Net chain theorem. Now let's start the next section, the substitution rule. Substitution rule. So substitution rule. Substitution rule. Okay, right now what we had to find antiderivative is using antiderivative table. Right now we will study a rule that actually to do so that we can deal with more complicated functions. So the idea, recall, in calculus we have differentiation, i.e. taking derivative, okay, derivative. Now and also we have integration. Yeah, inverse problem, okay, they're inverse integration. Okay, so here we have a derivatives of a function. And then here we have antiderivative. Now they are inverse operation. Now here we have tangent problem. Here we have area problem. On this side we have derivative. This side we have antiderivative. Derivative, differentiation table, derivative table. On this side we have antiderivative. We write the derivative backwards. Okay, switch the input with output, then we get antiderivative. For instance, we have certain rules here. They are inverse. Okay, so we have the corresponding rule. So we have product rule. The rule in product rule. What the corresponding thing for product rule in differentiation? Okay. Now this corresponds to integration by parts. Integration by parts. Something called integration by parts. And here, what is chain rule? chain rule in differentiation, we have a chain rule. Chain rule corresponds to a rule called the substitution rule. The substitution rule. Okay. Let's recall what the chain rule says. Let's recall what the chain rule says. So chain rule. Let's start a chain rule. The chain rule. The chain rule says if we have for instance, outer function is capital F, inner function is ux. Okay. Then if we differentiate, so let y be the thing. Then dy over dx, this we need to find inner derivative and outer derivative, multiply them together. So this will be df over du times du over dx. Okay. For example. So suppose y is sine x squared. Okay. So it is two layers. So we input x, the first inner function is squared, and then we get u to be x squared. And then we plug into the machine sine, then we get a sine u, which is a sine x squared. So this is equal to y. Then we get dy over dx is, you see, dy, then we get dy over du times du over dx. Chain rule, the chain rule. We apply the chain rule. Okay, then, this is du over dx. Okay, then what we get is dy over du. What is dy over du? Dy over du. Y is sine u, dy over du. So you see dy over du is d of du of sine u. Then we get a cosine of u. Okay, so this is cosine of u multiply du over dx. U is x squared, u is x squared. Then we get a du over dx, du over dx, which is twice x. Okay, multiplying twice x. And then we're reducing to x cosine, so we get a twice x multiply cosine x squared. Now, how do we do antiderivative? Now, if we do antiderivative, we need a, so what is antiderivative? 2x dx. Okay, now if you write from the chain rule, look at the chain rule, the line dy. So this side, this direction. If we go this manner from left to right, then this is chain rule. Okay. Now remember, antiderivative inverse. Okay, is inverse. So we should go from right to left. If we read it from right to left, then this gives us the substitution rule. Okay. So if we find antiderivative, this is we already know we find an antiderivative. Cosine, this is the sine x squared. We already have that thing. Plus constant c. Now if we do it in this manner, just because this definition, because we just checked this y equal to sine x squared has this derivative 2x times cosine x squared. If we find any derivative, then we get a sine x squared. Okay, now what we do is this thing. 2x is du over dx. So this is actually, if you switch, this is a dy over du times du over dx times dx. Du over dx gives us is 2x. Now dy over du is cosine x squared. Okay, cosine x squared. Okay. Dx corresponds to dx. Okay, so what you do is this. This is dy over du over dx times dx. Okay, so we write the thing backwards. We write chain rule backwards. Okay, by apply chain rule. So du over dx, you see, du over dx times dx. Okay, cancel dx, cancel dx, cancel dx, cancel dx. Because here dx comes from in denominator and numerator. Okay, so dx cancel denominator. So we get dy over du times du. Okay, times du. Times du. Then we cancel du, cancel du. Okay, cancel du. Cancel du. Du is in denominator and numerator. So we get a this thing. Now finally, d and this thing cancel each other. Cancel each other. They are inverse, cancels each other. Okay, and then this cancel each other. Okay, cancel each other. They cancel each other. Cancel each other up to a constant. So this we get so you see if you cross out d and in this integral, cross out this d and the thing, you get y plus constant c. What is y? Y is given by sine x squared. Let's see. Okay. So if you write chain rule backwards, then you get a substitution rule. Okay. 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 What we do is we write chain rule backwards, then we get a substitution rule. Okay, substitution rule. Now it's better when you use chain rule, try to use Leibniz notation. Okay, try to use Leibniz notation. Try to use Leibniz notation. Okay. The substitution rule says the following. The substitution rule. Okay, suppose we have so suppose we have this thing, substitution rule. Substitution rule. Substitution rule, we write, you see, suppose we have a function f as a function of ux, and this is u prime, multiply u prime dx. So you can write this thing. This is the, write u prime as du over dx. So this is f of u du over dx times dx. So dx cancel dx. So this you get as fu du. Okay, fu du. Okay. So you get f ux u prime of x dx. This is the fu du. Substitution rule. Okay. Let's see some example. This example. X cubed cosine x power 4 plus 2. Dx. Okay. Now, this is not in the antiderivative table, this function. Now, what we do is we use substitution. Now, what the factor that we substitute? What are the factors that we substitute? Okay. The general principle is when we use substitution rule is we should try to simplify the problem. So what we substitute more often is the complicated one, the complicated factor. Okay, so here we choose let u be x power 4 plus 2. Then du over dx. d over dx. This will be take the derivative d dx x power 4 plus 2. Then we get 4 power x power 3. Now 2 has derivative 0. So we get du will be du over dx times dx. Okay, now du over dx, this will be du over dx for x cubed dx. Now you see here we have x cubed dx. The original integral. Okay, so if we write this thing as this manner, we switch. Remember, multiplication is commutative. Now the relation of the integrand with dx is multiplication. So you see we have x cubed dx. We have x cubed dx. Now we solve x cubed dx. So which is divided by the coefficient 4. So this is a quarter d of u. On this we get substitute the bracket, the parentheses by u, cosine u. So and then 1/4 you can factor out. So it's 1/4 cosine u du. Now cosine u du is in the antiderivative table. So this is 1/4 sine of u. Once we're done, we place constant c. And then last step, return to original variable. Return to variable. Original variable x. So this is 1/4 sine u is x power 4 plus 2 plus c. Then we are done. For this problem. Then we're done. Now you can check answer use differentiation. You can check this answer use differentiation. Okay, example. More examples. Let's see this example. 2x square root 1 plus x squared dx. Well, if you at the first sight, this function is not in the antiderivative table. So what we want to do is we use substitution rule. We will try to use substitution rule. Now, what factor do we substitute? Now, you see from the example that which factor that cause trouble? You see the factor 2x. 2x is polynomial. Okay, 2x is polynomial. Polynomials are easy to deal with. So we do nothing with the easy part, 2x. Now the complicated part, the square root 1 plus x squared. Okay, so a natural choice to substitute is let u be 1 plus x squared. Okay, let u be 1 plus x squared. Then du over dx, take a derivative, will be d dx 1 plus x squared. Take a derivative of that thing with respect to x. Derivative of 1, we get 0. Derivative of x squared, we get 2x. So this is 2x. Then we get a du. What is du? Du is du over dx times dx. Okay. Du over dx is 2x. Okay, du over dx. By last step, we get du over dx 2x. Multiply dx. Then you see we have the factor 2x dx. You see the integrand, we have factor dx. Okay, we have 2x dx. So if you write switch multiplication, okay, because multiplication is commutative. Okay, you see we have 2x dx, which is exactly du. Okay, which is exactly du. We substitute 2x dx by du. Okay, substitute dx 2x dx by du. Now the square root will becomes substitute the square root. Okay, remember u is 1 plus x squared by our substitution. Okay, so this now becomes power antiderivative square root u. Okay, then we use power rule, increase power of 1 and then divide. Plus constant c. Then this we get a u to the power 3 over 2. Divide 3 over 2, so we multiply 2 over 3. Okay, flip them. flip, okay, plus constant c. And then the last step, return to original variable, return to variable x, variable x, variable x. So this will be 3 1/3 2 over 3. Now u is 1 plus x squared over to the power of 3 by 2 plus constant c. You can check the answer by differentiating this. Okay. Now a little more complicated example is we modify a little bit. We modify this a little bit. Okay, the integrand is square root of 1 plus x squared times x to the power 5. Okay, the first side, from our first side, this is not in the integrity table. So we should try to use something else. We use substitution rule here. Now, the next question is, what substitution factor do we choose? What substitution factor that do we choose? Now, as we mentioned earlier, the power x to the power 5 is easier to deal with. So this thing we keep it fixed. We do nothing to that thing. And the more complicated factor is 1 plus x squared. So we will try to substitute 1 plus x squared. Okay, then we let u be 1 plus x squared. Then du is du over dx times dx. Du over dx is derivative of u with respect to x. Du over dx, you see, du over dx, which is 0 plus twice x, which is 2x. Then du over dx, we got 2x times dx. Okay, so du, we have x dx. So we can, now if we compare the original problem, we have x to the power 5. But here, the du, we have x dx, okay, up to coefficient 2. Okay, now how do we deal with power 5? Power 5. Now remember, when you do substitution rule, you should substitute everything. Substitute everything, including the integrand, including the differential, okay? Including the differential and the integrand. Now what do we use the following trick. X power 5, we can write as, we split a factor of x, so that we have x dx. And then x power 5, then we get x power 4, this is the thing. Okay. Now x dx, we can solve x dx, okay, solve x dx. Then we get x dx is divided by 2. Divided du by 2. Or multiplied by 1/2. So this is 1/2 du. Okay. Now integral just integral. Square root of that thing, we substitute that thing by u. Okay? Because u is 1 plus x squared. Now what do we do with respect to this x power 4? How do we find a relation in terms of u? How do we solve x power 4? Find a relation between x power 4 and u. Remember, u is 1 plus x squared. Then u minus 1 is x squared. Okay, if we know x squared, how do we find u to the power x to the power 4? Well, we just square both sides. Okay, so this will be u minus 1 squared. Then what we do next is we expand, so that we expand the thing, so we get its degree. Okay, this is u square root of 1/2. Square root is 1/2 power. Now u minus 1, we can write u squared minus 2u plus 1. Don't forget it's 1/2 du. factor is 1/2 to factor out. So this then expand, then apply power rule. Expand, this is the u to the power 1/2 plus 2, 5/2, minus twice u to the 1/2 plus 1, 3/2, u to the 1/2 du. Then apply power rule. Okay, all antiderivative. So this is 1/2 times u to the power 5/2, increase power by 1, 7/2, and then flip. Okay, 3/2, increase by 1, 5/2, and then flip. Okay, now 1/2, increase power by 1, 3/2, and then flip. Once we're done, put constant C. Okay, and then simplify this, multiply 1/2 inside. So this will be 1/7, u to the 7/2 minus 2/5, u to the power 5/2 plus 1/3, u to the 3/2. Let's see. Then return to original variable. Return to variable x. 1/3, u is 1 plus x squared, 7/2 minus 2/5, 1 plus x squared, 5/2, plus 1/3, 1 plus x squared, 3/2, plus c. Okay, you can of course check this answer, use differentiation. Okay, more examples. Tan x dx. Tangent x dx. What substitution do we use? Well, this tangent x, a technique to deal with trig. Okay, first of all, this tangent x, we haven't done it yet. It's not in the entry table. So if tangent by definition is sine x over cosine x dx. Okay, now we use substitution. Now, once we have a fraction, what we usually substitute is either denominator or numerator. Most often, we either substitute the denominator or numerator. Okay, now here we substitute the denominator. So we let u be cosine x. U be cosine x. Now what is du? Du over dx, take a derivative. Du over dx, cosine derivative, what do we get? Negative sine x. Okay. Now du, what will be? Du will be du over dx times dx. This will be du over dx negative sine x times dx. You see, exactly we have sine x dx. Okay, sine x dx. Okay. So if you write this thing as, so sine x dx will be, so if you write this thing sine x times dx over cosine x. Oops. Okay. This will be negative du, okay, negative du over cosine x, substitute cosine x by u, okay. Now this is negative du over u. You can also write in this manner, negative 1 over u times du. Okay, 1 over u is antiderivative. We already know that. It's negative ln. Okay, negative keep fixed. absolute value of u plus constant c. This is negative ln u is cosine x. Let's see. Okay, now what we often do is we put this -1 inside as a ln, put a cosine x to the power of -1 plus c. This will be ln 1 over cosine x. Now 1 over cosine by definition is ln secant, okay? 1 over cosine by definition is secant. So finally we get this is antiderivative tangent. We get ln secant x absolute value plus constant c. Okay. Okay, maybe this file is too big. Let's start a new notebook, start a new section. Okay. All right. More examples of substitution rule. All right. More examples. Okay. Okay, what we substitute for this example is not in the antiderivative. What we substitute is let u be 1 plus 2x. Okay, then du over dx will be d dx 1 plus 2x, which will be 2. Okay, so we got du is du over dx times dx. Du over dx is 2. Okay, so it's 2 times dx. So you get 1/2 of du will be dx. Okay, so you get this dx. This will be the square root you replace by square root of u. Okay, now dx is 1/2 of du, 1/2 of du. Then you factor out is 1/2 the coefficients. Now square root of u as u to the 1/2 power. Then this will be 1/2 times u is power. Okay, increase power by 1. 1/2 increased by 1, so we get 3/2. And then divide. So we multiply the reciprocal plus constant c. So this will be 1/3. 2 cancel 2. Now u to the 3 over 2. U is, remember, 1 plus 2x to the power of 3 over 2 plus constant c. Then we're done with this problem. Okay. Okay, more example. Well, this example, first of all, the integrand is polynomial. You may ask, okay, for polynomial, we can always expand it. And then apply power rule. Okay. In theory, we can do it in that manner. But in practice, this power 9, if you expand that thing, it will be really ugly, the algebra. So we will avoid that thing. Instead, we will try to use substitution rule. So here we let u, so x squared is polynomial, is easy. Let u be, so we substitute the complicated factor, u be x cubed plus 5. Then we get du over dx, take a derivative, du over dx is Now x cubed, if you derivative of x cubed has derivative 3x squared. 5 has derivative 0, so this is 3x squared. So you get du will be, du over dx times dx. Du over dx, you get a 3x squared times dx. So here, if you look at the original problem, we have x squared dx. Okay, so we have x. So if you write in this manner, switch. Okay, switch the order of multiplication. Multiplication the commutative, you can switch the order. X squared dx. Okay, so you get here x squared dx divided by the coefficients 1/3. You get a 1/3. Multiply 1/3 to both sides. You get 1/3 du. So then you apply substitution. U is x cubed plus 5. So you substitute that factor by u to the power 9. X squared dx. X squared dx. So you substitute that thing by 1/3 du. Substituted by 1/3 du. Okay, so this is 1/3 factor out. U to the power 9 d of u. Now this is you apply power rule. Increase power by 1, so we get power 10, and then divide, plus on c. And then the last step, simplify this, return to original variable. 3 times 10 gives us 30. U is x cubed plus 5 to the power 10. Once we're done with plus constant c, then we are done for this problem. Okay, then we're done for this problem. More example. E to the sine theta, cosine theta d theta. Okay, what do we substitute? There are, the choice, when you do substitution, the choice, what factor that you choose to substitute is not unique. Okay, it's not unique sometimes. Okay, so here, what a choice do we choose? You see, we have sine, we have a cosine, we have e to the sine. Okay, so what we do is we choose, so the general principle when you choose a substitution factor is, it is to simplify the problem. So let u be sine theta. The reason that we choose sine theta is, if you differentiate du over d theta, then you get a cosine theta. You see, the factor cosine theta indeed appears here. Okay, if you choose as cosine theta, then you have trouble because sine theta is in the exponent. It's not directly multiply the d theta. Okay, so you get a du will be du over d theta times d theta, which will be cosine theta d theta. You see, we have cosine theta d theta, we have cosine theta d theta. Okay, they are exactly identical. So this means our substitution factor is good. So then we substitute. So we substitute the sine theta by u. Okay, so we get e to the u. Now cosine theta d theta, then we get a du. Okay, then we get a du. So we get a du. Then we get a du. So this is actually du. Okay, then we get du. So e to the u du. Well, that's in the entry table. So we just check entry table. So it's e to the u itself plus constant c. Last step, return to variable theta. Theta, variable theta. So e to the sine theta plus constant c. Okay, maybe let me stop here for today.